What if I told you that one of the most powerful machine learning models is built entirely on weak, unstable, overfitting decision trees, and somehow that makes it stronger? Today I'll explain random forests, not with surface level definitions but with real intuition, theory, maths, and engineering insight. Random forests are an assembled learning method, meaning they combine many weak models to create one strong model. Instead of relying on a single decision tree, which is unstable and prone to overfitting, random forests build many trees and combine their predictions. Assembled learning works like group decision making. One doctor can misdiagnose you, 10 doctors giving their opinion is far more reliable. Random forests achieve this strength through 3 pillars. Bootstrap sampling. Each tree is trained on a random sample of the dataset, drawn with replacement. This means the tree sees a slightly different version of the data, creating diversity. Random feature selection. At each split, a tree considers only a random subset of features, preventing trees from becoming too similar. Aggregation. Once all trees make predictions, the forest combines them. With classification, it's a majority vote. With regression, it's an average. This aggregation dramatically reduces variance and stabilizes predictions. Bagging is bootstrap plus aggregating. So bootstrap is when you create new datasets by sampling from the original dataset with replacements. Aggregation is when you train a model on each dataset and then combine their predictions. This reduces variance and increases stability. Random forests use bagging to create diverse trees. Variance is how sensitive a model is to small changes in data. High variance is when the model changes drastically if the data changes slightly. The model memorizes the training data, which then leads to overfitting. Decision trees have high variance, which is why random forest exists. For example, an analogy is a student who memorizes the textbook word for word, and if the question changes slightly, they'll panic. Low variance is when the model is stable. Small data changes don't affect it much, and it generalizes better. An analogy is a student who understands the concept. They can handle new questions easily, and random forests reduce variance by combining many trees. Generalization is how well a model performs on new unseen data. High generalization means it performs well on training data, new data, and this is what we want. Low generalization means that it performs well on training data and badly on new data. This is overfitting. Random forests improve generalization by reducing variance. Aggregation is combining the predictions of all trees. Again, for classification, it's majority vote, and for regression, it's an average. Aggregation reduces variance and stabilizes predictions. Hyperparameter is like a rule or instruction you give the model before it starts learning to control how the model learns. For example, how many trees to build, how deep each tree can go, how many features to consider at each split. We choose hyperparameters because they control model complexity, generalization and memorization, training speed, randomness, and overfitting prevention. By replacement, I mean, for example, if the dataset is A, B, C, D, E, a bootstrap sample might be A, C, C, E, B. Some points repeat, some disappear. This randomness creates different datasets, which leads to different trees and more diversity. Correlation is how similar the trees are. High correlation means that the trees make the same mistakes because they saw the same data, they use the same features, and they split it in similar ways. If all trees are similar, combining them doesn't help. Low correlation means that the trees make different mistakes because they saw different bootstrap samples, they use different subsets of features, and they split differently. If trees are diverse, combining them cancels out the errors. Bootstrap sampling and random feature selection reduces correlation. Parameters are learned automatically. Hyperparameters are chosen manually. Without choosing hyperparameters, the model would either overfit, underfit, or behave unpredictably. For example, analogy is baking a cake. The parameters is how much the cake rises. The hyperparameters would be the oven temperature or baking time. Good hyperparameters equals to a good model. Bad hyperparameters leads to overfitting or underfitting. Random forests work because each tree is weak and noisy. A single decision tree overfits and is unstable. But each tree sees a different version of the data because of bootstrap sampling and random feature selection. So each tree makes different mistakes. Their errors are not correlated. When you combine them, the errors cancel out, like averaging many noisy opinions. The result is a stable, accurate model with low variance and high generalization. The key parameters is an estimators. So how many trees to build. More trees equals more stability, but slower. Max depth is how deep each tree can grow. Deep trees leads to more complexity and more overfitting. Shallow trees are simpler and lead to less overfitting. Max features is how many features each tree can use at each split. This increases diversity between the trees. For bootstrap, if you turn it off, the trees see the same data. The trees become similar and correlation increases. Turning it off makes the trees more similar, which leads to worse performance. Minimum samples split. This is the minimum samples required to split a node. The higher it is, the fewer splits, the simpler the tree. The lower it is, the more splits and more complex tree. The minimum samples leaf is the minimum samples in a leaf. The higher it is, the smoother the predictions. The lower it is, the more detailed and more risk of overfitting. The random state controls the randomness in splitting datasets, initializing algorithms, or generating random numbers. It's needed for reproducibility. A decision tree is basically asking which question should I ask to best separate the data. To choose the best question, which is a split, it tries every feature and every possible threshold. It picks the split that creates the purest groups. A group is pure if it contains mostly one class. For example, if a node contains 100 samples, 50 cats, 50 dogs, it's impure. If it contains 95 cats and 5 dogs, it's pure. And to measure purity, trees use Gini impurity and entropy. The best split is the one that reduces impurity the most, which is called information gain. Random forests are naturally robust because the trees split on the most useful features. If a feature has missing values, the trees can simply avoid splitting on it. Many trees means that the noise cancels out. If one tree is confused by noise, others won't be. Trees don't assume linearity because they don't need clean, scaled, or normalized data, and trees can root missing values. Some implementations send missing values down both branches with weights. This is why random forests work well on real messy datasets. Random forest can tell you which features matter the most in two ways. Gini impurity, which measures how much each feature reduces impurity across all trees. If a feature is used often to make good splits, it has high importance. And permutation importance. You shuffle one feature and see how much the model performance drops. If the performance drops a lot, that means that the feature was important. What this formula means is that if the trees are similar, which is high correlation, the forest doesn't improve much. If the trees are different, which is low correlation, the forest becomes very strong. The more trees, the lower the variance. Random forests reduce correlation using bootstrap sampling and random feature selection. Here is the difference between random forest and gradient boosting. For example, XGBoost. A simple analogy is for random forest, many students answering independently is majority vote. For gradient boosting, one student learning from mistakes step by step. And here you can see when random forest is used and a real life example. Random forests are extremely robust because they handle missing values, handle noisy data, nonlinear relationships, high dimensional data. They require little pre-processing, are resistant to outliers, they rarely overfit, and work well on tabular data, which is most like real-world data. The limitations is that it's hard to interpret. You can't easily explain why the forest made a decision. And it's slow for very large datasets. Hundreds of trees is very heavy to compute, which makes it memory intensive, so storing many trees takes up a lot of RAM. And it's not ideal for sparse high-dimensional data. Models like SVMs or linear models perform better on text data. You're a lot smarter than you think. Machine learning is not about memorizing definitions, it's about intuition.